Our next section is section 5.5, more about roots. In this section, we have the definition of derivative of a function, and we also prove that if characteristic of f is p, then an irreducible polynomial, if we name it as f of x, it should be of the form g of x power p. Then in that case, you have this polynomial having multiple root, and we also prove that every finite extension is a simple extension. So these are the points that we need to discuss in this section, but in this video we are going to just have the definition of derivative of a function f of x over f, and we are going to have a lemma which proves the sum rule, constant multiple rule, and product rule given two functions f of x and g of x in fx. So first we have the definition of derivative. If we are given f of x to be this polynomial, then the derivative of f of x is written as f dash of x, and it is the polynomial. So you have all these are in the lower class itself would have studied. So this is when you have, say for example, x cube, your f of x is say x cube minus 3x square plus 2x plus 7, say for example, then the derivative of this is 3x square minus 6x plus 2. So the derivative is nothing but whatever here you have power. So this n x power n minus 1, then n minus 1 alpha n minus 1 x power n minus 2, and so on. And the previous one, this is the constant term. The previous one is nothing but alpha 1 x. So when you differentiate that, this is what you get. So the first lemma in this section in Herstein, it is 5.5.1. That gives the sum rule. You have sum rule which says that f of x plus g of x, the derivative of that is derivative of f of x plus derivative of g of x, and the constant multiple. When you consider this on the, you have that to be alpha into f dash of x, that is the derivative of f of x, and the product of this is nothing but the product rule says that first you find the derivative, just keep this one as such, plus then you keep this as such, then find the derivative of that. So these are sum rule, constant multiple rule, and product rule that we are going to have in this lemma, having given f of x and g of x in fx, and of course alpha is in f. Now we'll consider two polynomials that we need. One is f of x we have taken as this with scalars alpha I is from f. It's a polynomial over f. So alpha i's are in f, and similarly beta j's are in f. All your j ranging from 1 to n, and here I ranging from 1 to m. So you have f of x and g of x you have considered. Now given two numbers by the law of trichotomy, either m equals n or m greater than n or n greater than m. So here we have considered m to be greater than n. So when we add these two, f of x plus g of x, this is what we get. Your m is greater than n. So you have, we have just written what are those two polynomials, and because m is greater than n, here m terms we have written, then n terms, and this one as such, so that we can club the coefficients of like powers here. This one will remain as such. So you have like this. Actually the bracket should be here. So alpha n plus beta n x power n plus and so on, alpha naught plus beta naught, when you add the map, because we have considered m to be greater than n. Now this is, for example, f of x, you have x cube plus 2x square minus 8 say, and g of x, this is x cube, so you have to have say 2x square, or say 3x square minus 7x plus 11. So when you add these two, f of x plus g of x, the higher degree we have as such, then we add these two, So 2 plus 3 into x square minus 7x, then 11 minus 8, so 3. So this is what f of x plus g of x is. So this is for the general case that we have written. Now we have to consider, what we need to prove is f of x plus g of x, the derivative of this is nothing but the sum of the derivatives. So derivative of the sum is sum of the derivatives. So we consider the left hand side. When we differentiate this, we get m alpha m x power m minus 1. The next one goes like this, and so on. Here when you write, it is n x power n minus 1. This constant will be untouched. So you have this up to the previous term which we haven't written here. It is alpha 1 plus beta 1 x. So on differentiation, that will give you just alpha 1 plus beta 1. We shall name this as 1. Now f dashed of x, the derivative of f of x. Here is your f of x. So when you find the derivative, this is what you get: m alpha m x power m minus 1, m minus 1 alpha m minus 1 x power m minus 2, up to this. Because even here, the previous term is this alpha 1x. And similarly here also in the next one, you have beta 1x plus beta naught. So when you consider the derivative, this is what you get for f, and the derivative of g of x is this: n beta n x power n minus 1, and so on. Beta 1, your m is greater than n, that's our assumption. Now you consider RHS. Find the derivative of f of x, we have found out. We need to find the derivative of g of x, we have found out. We have to add them up for the RHS. So when you add them up, this is what you get: m, because m is greater than n, first we are writing that, and then the rest you have. Even this one here, instead of writing this, you have alpha 1 plus beta 1 is written here, so that is, this is redundant. You have n here, n alpha n x power n minus 1, the coefficient of that we need to collect and write, so that is what is done here. So all the terms that we have got. Now you consider equation 1 and equation 2. Both are the same: m alpha m x power m minus 1, m alpha m x power m minus 1, m minus 1 alpha m minus 1 x power m minus 2, and so on up to alpha 1 plus beta 1. So that proves the first rule, namely sum rule. Next we have, if we consider f of x to be this, alpha times of that will be this. When you find the derivative of this, you have m alpha beta m x power m minus 1 plus, and so on, m minus 1 alpha beta m minus 1 x power m minus 2, and so on, plus the previous one. If you have written, should be here, it is beta 1x, and here it is alpha times beta 1x. So you are just left with this. So naming that as 3. When we consider f prime of the derivative of f of x, which we have as m beta m x power m minus 1, m minus 1 beta m minus 1 x power m minus 2 up to beta 1. So when you multiply it throughout by alpha, this is what you get. From 3 and 4 we have this. Now coming to the third one, writing this f of x as a big expression like alpha m x power m plus and so on alpha 1x plus alpha naught, and then g of x as say some beta n x bar n plus and so on beta 1x plus beta naught, and then multiply. The process will be very big. So instead of that, we mainly concentrate on the powers of x. So the general power here we shall name it as say x bar I, because constant is untouched by the derivative. In fact, the derivative of a constant is only 0 if you apply the product rule. Product rule only is established now. So f of x into g of x, to have what is this, we consider a representative here x bar I, and here the representative as x bar j. So that f of x, the derivative will be I x bar I minus 1, and here j x power j minus 1. So when you consider f of x into g of x, it is x bar I, f of x into g of x will be x bar I into x bar j. So that is x bar I plus j. So when you find the derivative of that, it will be this. And when you consider f of x, g prime of x, f of x is this, g and the derivative is this. So you have this x bar I, this is f of x is x bar I, and g dashed of x is j x power j minus 1. So when you add the integers, this is what you get, I plus j minus 1, and this j retained as such. And here you have again for f dashed, you have I x bar I minus 1, g of x is as such x bar j. So when we add the integers, we have I plus j minus 1 I. And in both these, this one is common. So taking that out, x bar I plus j minus 1, we are left with I plus j. So if we name this as 6, from 5 and 6, both are the same. So from 5 and 6, we have the third rule, namely product rule follows. Now in the next video, we will have this result, lemma rather. F of x has multiple roots if and only if f of x and its derivative have a non-trivial common factor. And we also have corollaries to this lemma. One is f of x is irreducible, means when we have characteristic of f to be 0, then f of x has no multiple roots. And if characteristic of f is p, then f of x has multiple roots, provided that f of x is of this form. And in the next corollary, we have characteristic of f is p, means then this polynomial has only distinct roots. So these this lemma and these two corollaries we will have in the next video. Thank you.